Good morning, good afternoon, and good evening to delegates attending from different parts of the world. Welcome to the fourth plenary session of 7th International Conference on Recent Advances in Geotechnical Earthquake Engineering and Soil Dynamics. In this session, we'll be having two keynote presentations one by Professor L. Gamal and the second one by Professor Charles Ng. This session will be chaired by Dr. G.R. Reddy and Dr. Vishwas Khatri. Before I hand over the session to chair and co-chair, I would like to briefly introduce our chair and co-chair. Our chair, Dr. Reddy, has vast research and academic experience. He has guided 10 PhD and 41 MTech students. His research areas are modeling techniques for complex structures, structure equipment interaction, stochastic methods, substructure techniques, etc. He involved in the design of several important critical facilities, including antenna for Chandrayaan project and Gamma Ray telescope, and many other. He has also developed products like dampers, isolator, and absorbers. He developed iterative response spectrum for nonlinear systems. He has 500 publications, including journals, reports, and conference proceedings. He has also authored a book titled Seismic Design, Structures, Piping Systems, and Components, published by Springer. As a president of Association of Structural Rehabilitation, he has developed guidelines. He collaborated in 35 research projects at the national and international level. Our co-chair, Dr. Vishwas Khatri, is currently working as assistant professor at the Indian Institute of Technology, ISM Dhanbad. He has worked on experimental and numerical modeling of geotechnical stability problems. He has authored as well as co-authored several journal and conference proceedings, both at national and international level. With this brief introduction, may I now request Dr. Reddy and Dr. Vishwas to kindly take over the session. Please, sir.
Okay, I think we will move to the next lecture by Charles, Professor Charles. Professor Charles WWNG is currently the Dean of H. Folk Ing Tong Graduate School, CLP Holdings Professor of Sustainability and Chair Professor in the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. He is the President of the International Society for Soil Mechanics and Geotechnical Engineering. I think currently also is continuing as a president of this particular society. Professor NG earned his PhD degree from the University of Bristol, UK in 1993. After carrying out a period of postdoctoral research at the University of Cambridge between 1993 and 1995, he returned to the Hong Kong and joined the university as assistant professor in 1995 and rose through the ranks to become a chair professor in 2011. Professor NG was elected an overseas fellow by Churchill College, the University of Cambridge, a fellow of Royal Academy of Engineering, a fellow of the Hong Kong Academy of Engineering and Sciences, and a Chanji Jiang Scholar, chair professorship in the Geotechnical Engineering. He is also a fellow of the Institute of Civil Engineers UK, the American Society of Civil Engineers, and the Hong Kong Institute of Engineers. So it is very great pleasure to welcome you, Professor Charles, for this particular session, and is also a great pleasure to introduce you to the the delegates as well as the organizers and others who are participating in this particular session. So I welcome again Dr. Professor Charles to start your lecture. Thank you so much. Thank you so much.
Thank you, Chairman, for your kind introduction. And if I may, let me share my screen.
So I request you see that your lecture is completed 40 minutes. I generally I don't try to interfere intervene in your lecture, so kindly take care of 40 minutes so that we have time for discussions. Thank
Yes,
you so
thank
much.
you.
Thank you so much.
Thank you. And before I start, I would like to thank the organizing committee for inviting me to make this presentation. And also, I would like to thank my co-authors, Dr. Tai and Dr. Vanswen, and for their contribution to the work I'm going to present. And due to the time constraint, as the chairman said, and I decided to move out anything to do with tunneling in my presentation. But in the written submission, and you will see in our paper, we cover both pile foundation and also tunneling, subject to normal faulting. So here is the content of my presentation. First of all, and I would like to briefly introduce my university because, as we all know, that the objective or function of a conference is to exchange technical information, but also to encourage collaborations among the universities, among the researchers, and also engineers. So I decided to give a little bit of background or introduction to my university so that I hope, and if you're interested in our university, perhaps we can establish different forms of collaboration. And then I'll move on to background of the research I'm going to present. And just in case you are not that familiar with geotechnical centrifuge modeling, which is the main tool that I use for our research, I'm going to present today. And then I'll move to show you say 3 sort of examples and using geotechnical centrifuge to solve different type of problem, including forensic engineering to investigate collapse of building in Shanghai, embankment widening using a 4S robot, and also a recent development of an environmental chamber for simulating climate change effects. Then I'll move on to 3-dimensional and centrifuge and numerical modeling of pile foundation subject to faulting, and present to you our interpreted measure and computer result. And hopefully I still have time, then I'll come to conclusions. And here's area photograph showing Hong Kong. Hong Kong is very small. If you landed to this airport here on the left-hand side, then travel to the east about 40 minutes, then we reach our campus on the east coast. And here a couple of photographs showing our campus and different view. I hope you agree with me. Our campus indeed looks very beautiful. And our university was established about 30 years ago, 1991, and we have 4 major schools. Our university is small, by the way. We only have 4 schools, about 10,000 undergraduate students and 50,000 postgraduate students, including 3,500 master students, and MSc students. But in the geotechnical group, and we are sort of pretty large. We have about 60 PhD students and 30 MPhil students. Although we are young, but we are sort of globally recognized for the time higher education young university, which means the university has to be below the age of 50. Then actually 2020, we ranked #1. And then QS ranking also, we ranked #2 in 2011. And good news perhaps to share with you is we are building a new campus in Guangzhou, and which is twice the size of the one we have in Hong Kong. And the Guangzhou campus is located only 27 minutes by high-speed rail from Kowloon to Qingsheng Station, which is very close in the sense by a fast-speed train. And English is an instructional language to be used in the campus mainly. And the new campus will be open next year, September 2022. And eventually we will have 6,000 postgraduate students versus about 2,000 research students in Hong Kong. So it's 3 times bigger in terms of research capability, in other words. And we will have about 4,000 undergraduate students, but undergraduate will start from year 3, okay? And then we will gradually increase to 4,000. And there's a couple of pictures showing the new campus from the architectural drawing. And that's how it should look like. And at the moment we are recruiting 150 academics, means professors, assistant professor to full professor above, okay? And also we are recruiting about 1,000 research students now. So if anyone interested in the audience interest, please go to our website. And talking about collaboration, and no matter whether it's Hong Kong campus or Guangzhou campus, we do encourage and exchange programs, meaning students from India can come to Hong Kong for 6 months, and our student can go to India for 6 months, and that will be fully funded by our exchange scholarship, and which now at the moment is about $1,200 per month, and is enough for a single research student. And also we have full scholarships for full-time students, depends on the types of scholarship, ranging from $2,000 to $3,500 per month. Okay, we also have a dual degree opportunity, meaning, say for some I.I.T if they're interested, can sign an agreement with our university. We have a dual degree program, meaning students can spend on each campus 2 years and to get a dual degree. And here's my research group, if you like. Okay. Oh, sorry. Beg pardon. And you can see actually my group is very international. I have a student from South Africa, from United Kingdom, Bangladesh, Thailand, and India. And he graduated 1 year ago. And then and also Iran, for instance. Okay. And also I'm student from Pakistan and also from a couple of African countries. So now let me move on to the background of the research I'm going to present today. And here are just a couple of pictures and showing a stadium in Turkey, which was hit and crossed by a normal fault, causing the vertical offset of up to 2.5 meters, causing a lot of damage, as you can see here. And Turkey is not the only location subject to earthquake and disaster. And this is a picture, just 2 pictures taken in Taiwan and Chi earthquake, and which is quite notorious and around the earthquake community. In 1999, again, you can see the fault ruptured of a building over there. And also this picture again taken in Taiwan, and due to the Chi earthquake and hitting the one of the continuous rigid foundation and supporting the high voltage electricity pylon. More pictures from Chi earthquake, and again you can see the damage of a 4-story building resting on a relatively flexible foundation, okay, by a thrust fault. So our design challenges and research objectives. Actually, the result I'm going to present to you actually come from actually initiated about 10 years ago by Beijing's city government. They really want to know, okay, for example, what is the influence zone at the ground surface due to fault movement, okay. Second question we will ask is, what are the remedial actions can be taken for existing pilot foundations? And what are the design criteria for new pilot foundations? And what should we do to rezoning for urban cities in earthquake-prone region or zones? So those are the design challenges we were imposed by the Beijing city government, and that obviously become our research objective. So we were commissioned to carry out over 30 geotechnical centrifuge tests. And this is a picture showing the interrelationship between centrifuge modeling, numerical modeling, and field monitoring. So geotechnical centrifuge is just one of the 3 tools that we use, okay, to tackle earthquake design problems or to verify new theory. So today I'm only concentrating geotechnical centrifuge and numerical modeling here. So What is geotechnical centrifuge modeling? Just in case you are not familiar with, I will just very briefly to introduce to you. The basic principle of geocentrifuge modeling is to recreate the stress conditions that will exist in a full scale, we call prototype, okay, using a model of greatly reduced scale. And how can it be done? This is done by subjecting model components to enhance body force, which is provided by a centripetal acceleration. So you can see here R omega square, centripetal acceleration, and conventionally equated to number of times of the Earth gravity. So NG. So NG is my surname. Now you understand why I do centrifuge, because my surname is NG. And mathematically, we can easily show that P is, subscript P stands for a prototype stress, okay, or initial stress, sigma, and in the field, it's rho G HP. And in a centrifuge, we can reduce the, say, dimension height, for instance, by n times. Then what you need to do is just increase the G level by n times. So you can get back the rho G HP. Okay, so the principle, as I say, is extremely simple. Now, therefore, the centrifuge is suitable for stress-dependent problems, such as consolidation, soil structure interaction problems, and like the presentation given by Professor Aguma, okay, soil structure interaction subject to earthquake, okay, and also liquefaction and slope stability, etc. Now, from a theoretical point of view, it's very, very important, okay, to get the stress right before we carry out experiments. Now, here's a plot of E log P curve, okay. For specimen A and B, they have the same Y ratio, that means same density. But if we carry out model test at 1G in the lab, that means low stress, here A, then the soil may contract, so the soil may dilate to the critical state line. That means we will be on the long conservative side versus the actual stress in the field, which we can represent it by point B. There is a high stress, okay? Actually, when you shear B, then you can contract towards critical state. So we get the opposite result, but on the long conservative side. That's why we must get the stress right before do experiment, okay? By subjective, let me go back, sorry, I beg your pardon. By increase the stress state from 1G to high G, so that the stress state at B is almost identical to the field. Right, of course, any physical model tests are subject to a number of scaling laws, okay, if not all. And one of the typical and most useful one, I would say, is consolidation, for example. Then, which is the time factor here, prototype divided by model is n squared. So that means if we carry out 1 day consolidation at 150 G, which is our optimal capacity of our centrifuge, then it will be equivalent to about 62 years of consolidation time. And in the interest of time, I will not go to detail about all this to bother you. So just quickly to introduce the 4 major principal applications. 1, modeling of prototypes such as slopes, tunnels, liquefaction, earthquake-induced problems, consolidation, etc. And recently also increasing use of offshore engineering such as wave and wind loading on wind farms, for example, and investigation of new phenomena and mechanisms, okay, such as explosion, plate tectonics, and again recently debris flows, climate change events, energy exploration such as exploration of shale gas and methane hydrate, for instance. And also we can use it as a numerical, similar to numerical tool to carry out parameter study in centrifuge. But I think the most important use of centrifuge, actually to me, is to calibrate numerical models and methods. Especially now the computer is so powerful, okay? how do we know our calculated results are correct? Okay. Now, very often I heard people say, okay, we calibrate against case history. But I do have a word of warning. Okay. And here we have field observation and we have computer program. When we get a good match, if we ask ourselves carefully, what does that mean? Okay. I think we have to be very, very careful to think about it because, okay, in the field, we have a lot of uncertainties. Okay. That's why the contractor claim the client use the word unforeseeable ground conditions, right? When in our numerical analysis, we assume K0, we assume water table, wherever it is, boundary conditions. And usually we assume, actually we don't know, right? And also we have a measurement errors, construction uncertainties, for instance. On the modeling side, numerical modeling side also, very often we assume, okay, and stress and strength, strength and stiffness, okay, is isotropic. Very often we ignore anisotropic phenomena in our modeling, right? We also assume the permeability is isotropic very often. And also we assume there's no coupling effect between stress and flow. So the good match in some way, I would say is quite fortuitous, okay, in some ways lucky. Now, I'm not saying numerical modeling is not good, okay? I'm just saying we must be very careful. Then how can we do better? My suggestion is we must calibrate, before calibrate case history, we calibrate physical model tests. Now, although 1G model tests cannot represent full scale, okay, stress, but 1G test still is very useful because for some, as I said, under low stress dilate. So if your model or model procedure or your model parameter are any good, should be able to capture the dilatancy of the event, right? So my suggestion is we go for the calibration of physical model test first before you calibrate a case history. Now, model tests in some ways good in the sense, although again, model tests cannot truly represent what happened in the field, cannot. But we almost know everything what we put in our model, our physical model. So there's no much uncertainty in our model tests, unless your student deliberately want to fool you, put a stone or a rock, okay, into your soil model. That's different matter, of course, right? So in theory, we are supposed to know everything in our model tests, so that gives you a lot of confidence, okay, provided your test is conducted properly. So this is my suggestion. Anyway, so this is our centrifuge in Hong Kong, and established in 2001, and it's a beam centrifuge. And when you spin out 8.4 meter in diameter, and can run to 150 G, and for earthquake problems, actually we in 2001 actually that was the first one biaxial shaking table and mounted on centrifuge, and we successfully did some tests and published in different journals. And also we have a 4S robotic manipulator data later on, and you will see this baby in operation, okay. And in one of the example I'm going to give to you. Okay, so if I may show you one first example, which is a forensic engineering to investigate. Actually, we were commissioned by a client in Shanghai to investigate the building collapse over there, and which is the building collapse you can see here. Okay, and there's a closer view of the collapsed building, and you can see the picture actually during the collapse. What happens? Also, just immediately before the collapse, what happens? This is the collapsed building, obviously. Then there was a bad filling on the right hand side, and then excavation on the left hand side. So this is a schematic diagram. Okay, let me. I don't know what happened to my mouse. Looks like hang up. Okay, looks like coming back. Okay, so immediately before the collapse, there was a filling up on the right hand side and also excavation on the left hand side simultaneously. So after the building collapsed, obviously different parties blame each other. That's why we were commissioned by the Shanghai government to investigate what causing the collapse. Okay, but anyway, I will not go to detail, but I just show you a video. Okay, and in order to save time, maybe I just go back to a okay. So I guess you can see I'm moving my mouse to speed up the present. So we idealize the geology in Shanghai, and what you can see here is a model pile and there's a building. Actually, we scale almost everything of the problem. So you can see the building of the ground beam here. Okay, there's a shear wall you can see from the top and insulation of the building in the centrifuge container. Okay, and now this is a video taken during one of the tests. Okay, so let me stop here for the time being. So we use a hydraulics actuator to simulate the filling of the surcharge on the right, and also excavation on the left. We're using a string out the heavy fluid, which is equivalent to the density of the soil. So this is the last stage of the test, if you like. Okay, you can see the building is moving and then collapse. Okay, so if I may just replay a little bit. Okay, now then if I go back to the presentation mode so that I can use the mouse. Okay, and so now you can see the upper diagram is the collapsed building in a centrifuge. The lower diagram is the collapsed building in the field. So I hope you agree with me. They look almost identical. And actually, after the tests, we can also take. We can carry out very detailed investigation where the piles were broken and how they were broken and so on. Okay, so you can see that a lot of detailed analysis here after the test, and also we can invest the mechanism. So if you are interested in this work, and it's published in Geotechnical 2019. And now another development, actually we use a robot to simulate the whitening of a embankment. Okay. Again, let me, in terms to save the time, so I will just speed up. So we use a robot and we designed this. Okay, let me explain a little bit. So we all know that in order to whitening of a embankment, then very often we put piles to support this new part of the embankment, and the pile is obviously try to minimize the settlement of this embankment, new part of the embankment caused by the consolidation of soil clay underneath. So now the question is, what should be the pile spacing, for instance, and should we use a geomet and so on and so forth? Okay. So in order to simulate this, of course, one can do three-dimensional numerical modeling, but as I already explained, we need to some sort of physical test to give us confidence the numerical modeling results in some way are reasonable. So we were asked by clients in the mainland, excuse me, to carry out a physical model test, and so this is the model part. It saves time. I will, okay, I skip that. So now this is the actually using robot to simulate the embankment construction. So this part here is the existing embankment on the right hand side, and now the embankment is being built, okay, bit by bit, layer by layer, so that we can properly control the speed of the construction, okay, in a centrifuge, which will mimic what have actually happened in the field. And also we can control the density of the filling material in a very precise manner by using a robot. Okay, so this is almost the final touch of the construction. And during the construction of the new part of the embedment, then pore pressure and SO strain and bending strain of the piles were monitored. Okay, I will skip that in the interest of time. Okay, and then, so let me move on to the third example. As we all know that nowadays the effects of climate change and become more and more evidence, okay, or severe, if you like. That's why we develop our sort of an environmental chamber in centrifuge. So what does that mean? Means we can control whether the humidity in the chamber, and heating and cooling unit means control temperature, and ring nozzles control rainfall intensity and duration, and fans means able us to model wind. Okay, sorry, let me go back. Okay, and then we have infrared and ultraviolet to control heat. Okay, so in our centrifuge. So here's a picture. Oh, sorry. So here's a picture showing the actual test in one of our experiments. Okay, so now you can see the humidity nozzle is being used. I use high resolution camera to measure the surface deformation and so on. And if you're interested, this is published in Geotechnical Letters 2018, and that gives you much more information than my presentation here. Okay, and I don't know why my computer play up a little bit. Maybe we have to wait for a little bit, couple of seconds. Now, actually, nowadays we use this environmental chamber to study freezing and flowing and effects on slope stability and also on an embedment.
What happened?
Like let's say on my laser pointer.
Yeah.
I guess now it's back to normal. Is it correct?
Yes, yes.
Okay, good. Okay, so now let me define the problem. I'm going to discuss with you. Okay, and so what we are looking at is it's either a single pile or a pile group. Okay, which is a 1x3 pile group. This is a plan view show here. Okay, and the location of this pile group and so is defined by the coordinate x in the horizontal direction, and also depth is that direction, and y is the second y-axis into the screen. And there's a very important dimension called S. S is measured from the free field rupture outcrop to the edge, the far end of the pile group, because this is defined as S in the x direction. And the width of the pile cap is called B. Okay, and we are going to use this dimension later in a minute. And as I mentioned right at the beginning, and I will not discuss anything about tunneling in this presentation due to time constraint. So what you are seeing here on the left is our model container, which and a single pile is installed, okay, in the container. So the model pile in prototype scale is a square pile, 0.65 meter, okay, on all sides. So it's a square pile, 0.65 meter. And the embedded depth into the soil stratum is 15 meters in prototype. Now the tests, all the tests I present today, and the those tests were conducted at 50 G, 50 times gravity, okay? And on the right-hand side here is the 1/3 pile group, okay? And you can see here on the left, we call PF on the footwall side, and for the hanging wall side is pH. In the middle is called PB, okay? And for simplicity, we use Toyota sand, dry Toyota sand, and all the tests, okay? And obviously, we work on the effective strength principle. So it doesn't matter whether saturate or unsaturated, sorry, saturate or dry. And we just work on the effective stress principle. So that's why we can simplify the problem without worry about the pore pressure here. Okay. And of course, our objective is not to study how the pore pressure dissipates in our experiment. Okay, that was not the objective. Okay, and then we use an LVDTs and also PIV whatever system to measure the settlement of the piles and also horizontal displacement of the pile, etc. Okay, and in interest time, I cannot go into detail. And now, very important is the model container. How can we simulate the fault movement? And there, I guess most of you know that there are two types of boundary conditions we can simulate. One is the one I just showed here, is horizontally kinematically unconstrained boundary. Okay, and also we can have rigid boundary. So for this horizontal kinematically unconstrained boundary, is we allow the soil body here on the hanging wall side can move freely horizontally and vertically versus a rigid boundary. Okay, but today I'm not going to present the rigid boundary test. But if you're interested, you can see from this Geotechnical letters published in 2015. Okay, they compare the effects of different boundaries on the performance. Okay, today I'll only report on the sort of horizontally kinematically unconstrained boundary result. And actually, those are the two model containers. One on the left-hand side here, ready to be tested. On the left-hand side is the single pile SP, single pile here. And here is a pile group on the right-hand side, okay? And the downward fault movement was controlled by there's a hydraulic cylinder hydraulic actuator beneath this loading pattern. Okay, and then during the tests, we created fault movement in 5 stages. Okay, and for each stage, we present in Polar scale 0.4 meter, 0.8, 1.3, 1.8, and 2.1 in this vertical direction. Okay, and before we allow the fault movement to take place, we apply and calculate, actually deduce working load for each single pile and pile group. So in other words, vertical load we apply vertical load first, then we allow for fault movement to take place. Okay, and after spinning down the centrifuge, then post experimental and observation were made, and then all the deformation and also the bending moment and on the piles and also the pile cap and actually were measured during the test. In addition to centrifuge, we also carry on numerical simulation. Okay, and so what you're seeing here, the upper two picture here, plan view, this is a single pile, and this is the elevation view of the single pile. And the single pile actually is located on the footwall side. And the lower two diagram is for the pile group. Again, this is a plan view and this is an elevation view. And here are the 3 piles. And this is a PF pile, and this is a PB, and this is a PH. Okay. And actually, now we use and the constitutive model is the one actually given in the flat 3D. It's a string softening more Coulomb with more Coulomb failure criteria. And obviously, this is continuous model actually is greatly simplified. Okay, cannot taking account of strength dependence stiffness, for instance. But we think it's probably good enough, okay, for our back analysis and also for our numerical parametric studies. And talking about parametric studies, so this is our plan for the parametric study analysis. And there are two series, one for single pile, the other one for pile group. Okay, and what we are trying to study is to answer the four, remember the four design challenges and objectives. Okay, so we in our numerical model, we let the location, we don't change the fault location, but we change the pile group location ranging from negative S to positive S. Okay, so that's why you can see here negative 15.5. Okay, this is S. Okay, and so on to positive 31.5 meter. Okay, so there's a range for the pile group, and similarly, there's also corresponding analysis for single pile, also from negative S to positive S. So now let me show you some results. Okay, and this is the development of ground surface settlement. Okay, induced by faulting. On the left hand side is single pile group single pile test, and on the right hand side is a pile group test. Okay, and we are seeing the horizontal axis is the distance to free field rupture outcrop. That means X. Okay, remember the horizontal distance defined as X, and here's a settlement. And this curve here is the corresponding measure. The open circles are the measured numbers. Okay, corresponding to 0.4 meter of and downward fault movement. And this one here 0.8, 1.2, 1.7, and 2.2. Okay, and similarly, and this is for the pile group. And then what we find actually in terms of ground surface settlement can be reasonably represented by an error function. Okay, here I show in here. And so obviously, but the coefficient of the error function then depends on whether single pile or pile group, also depends on the magnitude of the fault movements. But broadly speaking, and that can be a very simple tool to be used to for zoning of the surface, ground surface surface of any urban city. And here on the right hand side here, a picture compare the mechanism between this is observed mechanism in centrifuge test. The upper one is single pile test, and for the single pile, and this is for the pile group test. Okay, on the right hand side, there's a numerical simulation here. Again, this is a single pile, and this is the pile group. Then what you're seeing a plotting of plastic shear strain. Okay, you can see well developed at the fault location here, and also you can see the pile group is bent and also tilt towards the right hand side. Now, one thing interesting finding is here is actually there's, although the initial fault direction actually we designed to investigate 70 degrees, okay, but actually the fault propagation is deflected to 80 degrees, okay, and then we suspect it's due to the dilatancy of the sand. That's the way use. And here a series of pictures. This left hand side here is the settlement of the normal fault versus the displacement of the single pile test, and this is a pile group here. Okay, let's start with single pile. Then we can see the settlement of the single pile. The black solid symbols represent the measured numbers, and the computer ones are the open symbols, represent open symbols. What you can see here, for the single pile, actually, the vertical settlement and measured vertical settlement actually compare well with the computer settlement using the flat 3D program, and the magnitude settlement magnitude increase as corresponding with the magnitude of the normal fault. Okay, but interestingly, what you see here, the horizontal movement actually is independent. Okay, so you can see here is independent of the magnitude of fault movement. So what does that mean? It means there's a rigid body translational movement horizontally. Okay, and that's a mechanism that we can identify. And how about the pile group here? Okay, then the right-hand side of the two figures are both showing the piles performance in the pile group. And so for each one, again, it's using the same symbols, notation here. Solid ones represent the measured, and the open circle represent the computed values. Although the measured and computed are not identical, and actually the computed one tend to predict more than the measured ones. But the general trend you can see actually for the pile group, okay, this is different, quite different from the single pile. For the pile group, actually, the settlement or the normal, the settlement of the vertical settlement of each individual pile is corresponding, in some way corresponding to the settlement of the normal fault. Okay, when normal fault increase and E increase, and also the difference between the measurements also increase. Now for the horizontal displacement of the pile group, different phenomena can be observed. You can see here all three piles, okay, measured ones here, they almost fall on the same line, and this all three piles from the computer results, again, they all fall on the same line. Okay, so what does that mean? Again, similar to the single pile, actually the horizontal movement in some ways is a translation of rigid body movement, but the vertical ones, okay, is different. It actually is subject to subject to tilting, and also subject to bending. Okay, in addition to translational movement. So obviously, because of that, then we induce extra bending moment in the pile cap, and also the pile SO pile load. Okay. Now let's move on to here's a plot of pile displacement versus the normalized distance away from this free field fault location. Okay, so S divided by DD is the diameter of pile, and for the pile group normalized by the width B, okay, of the the breadth of the pile cap. What you are seeing here, and certain three distinct zones can be identified. For example, in zone 1 here, what you can see here, there's no much, so if the pile is located in this zone 1, okay, then basically, no matter what the fault movement is about, actually, there's not much movement. But if the pile is located in zone 2, okay, which is -10 to about 3, okay, then you can see actually about 0 location, both the tilting, vertical settlement.
Professor Charles, sorry for intervening.
Yes.
Charles. Hello?
Yes. Yeah.
Please. Please.
Okay. I will do my best. Okay. So you can see there's 3 distinct zones can be identified. Okay, and this is transition zone, and creates a larger differential settlement, and that's what designers should be pay attention to. Okay, once you go beyond the zone to go to zone 3, then you can see that actually the pile settlement is identical to the applied fault movements, and horizontal is half, and tilting is further. Actually, it's not much tilting in this zone here, so this is relatively safe zone, if you like. Okay, and similar picture also emerged in the pile group. Okay, so the take home is there's 3 distinctive zones can be identified. Now we were looking at the settlement, but also we can look at the pile loads in each pile each pile of the pile group. Again, 3 distinct zones can be identified. Now remember the pile cap the surface load is applied to the pile cap before fault movement is allowed to take place. So this is the working load is about 1100 kilonewton. You can see within zone 1 there's no change. Okay, and then but within the transition zone here, okay, and different piles. So here represents 3 different piles of the symbol here. So within this within this zone, the pile subject to change from compression to tension, for instance, for the PP pile. So this is important, very important for the designer to think about how to take care of this tension, okay, or even additional loading, compression, okay, if the pile group is located within zone 2. And for the zone 3, there's no much change. There's no redistribution of axial forces. Okay. And again, for the tilting theta, the same thing. Okay, it's only the zone 2 is affected. Okay, so the initial time will not go through that. Now, for the bending moment, again, it's very clear. This is for the PF pile, PB pile, and PH pile. Okay, the zone within the zone 2, if your pile group is within zone 2, and actually the bending moment can exceed about 6 times the design ultimate capacity of the individual pile. So definitely designers should be paying much attention to if your pile is within the zone 2. Okay, so let me just quickly summarize what we sort of identify. Certainly, for designers, one is very clear. There are 3 zones can be identified. One is called safe zone. I call zone 1. There's no significant displacement or tilting or settlement need to be aware about in zone 1. But zone 2 is the transition zone. That's where the trouble zone, if you like. Okay, and definitely the designer should pay attention if your pile foundation is located in this zone, or if you try to plan your zoning for buildings, etc., then you have to pay attention whether your zoning fall within the this transition zone. And then the last zone is a translational zone. It's a rigid body zone, if you like. Okay, and there's we see a displacement and translationally, but without tilting, for instance, for the pile group. And the demarcation of the 3 zones is not affected by the magnitude. Okay, that's important, by the magnitude of fault movement. That's good, and also it's good news. Okay. And here, just give you more detail and elaboration of in the transition zone, the tilting and associated bending moment. Okay, of the pile we investigate, which the peak value. Okay, the transition zone is always a problem. Okay, and also the tilting of the pile can exceed the ultimate allowable limit imposed by EC Roorkee 7, for instance, and the maximum bending moment, okay, of all piles in transition exceed, okay, can up to 5.8 times the ultimate capacity. So obviously, increase of thickness or reinforcement should be considered in the design of the structural capacity of the pile and also pile cap. Okay, and the computed maximum tensile force in the middle of the pile group, okay, that's PB, okay, exceed the ultimate tension capacity up to 57%. Again, the tensile stresses must be taken into consideration in the design. Here's a list of relevant, I would say, 8 publications. And if you are interested in the work I just present, please just take a quick look. And if you do need these papers, and let me know. And thank you for your attention, and I apologize for a bit of overrun of my presentation. Thank you.
Oh, thanks, Professor Charles, for giving a very elaborate lecture on the centrifuge test, considering the 5 pile foundation subjected to the normal faulting. I request Dr. Viswas to have quick questions. Maybe I hope organizers will allow for 5 minutes. Professor Ravi, is okay 5 minutes for question answers?
Yeah, one or two quick questions, sir, because our other session is going.
Yeah, please, Dr. Viswas.
Started.
Yeah, Dr. Viswas, please go ahead. Question answer sessions.
Till now, I think I have not received actually the question which is available, that is from the old session.
Yeah,
which we have
maybe I think I'll just summarize a given very wonderful lecture by giving introduction to the Hong Kong University, then also given a lot of pictorial presentation of various actual structures subjected to the normal faulting, how they behaved. Then he introduced, about the centrifuge test. Also, shown the test on the structures with the pile foundation with the horizontal excitations. Then he focused on the normal faulting effects on the pile foundations. It was a very, very learning lecture, and it is very.
May I say something? Thank you for the organizer for inviting me to this presentation. And also I'm very glad to see my good friend and Professor Aguma here. And I listened to his presentation, and his presentation also very interesting. I hope we can develop some collaboration, physical numerical modeling together. Professor Aguma visited our campus some years ago.
Absolutely, absolutely.
Yeah.
My pleasure.
Yes,
Yeah, let's
yes,
keep in
please.
touch. Hopefully we
Dr.
can.
Viswas, do you have any questions, Dr. Viswas?
no, sir, I have not received any.
Okay, I have a small question to Dr. Charles. One is when you have a horizontal excitation.
Sorry, I can't hear.
Model frequency.
Sorry, there's a connection problem here. I cannot. Sorry, I think there's no connection. There's a connection problem.
Dr. Reddy, there is some network problem at your end.
Yeah, I cannot hear.
I think
his face is freeze.
No problem.
Maybe he can write to me. Okay, I don't want to bother you.
Later. If there are no questions, I think I thank
Oh.
Yeah,
Okay.
I think Dr. Reddy has thanked all of you.
Just I wanted to.
Yeah, please.
I think, I have also used the centrifuge data. Nice to see that. I have worked one problem in my PhD, that is on scale effect on the foundation problem, where I have used the centrifuge data, and ironically, I have also used the Toyota sand only. So this was just nice to see again revisiting the old things.
Yeah, after COVID-19, you are most welcome to visit us.
Yeah. Thank you, sir.
Thank you. Thank you.
Yeah. May I take the session, Dr. Vishwas?
Yes. Yes.
Okay. Thank you. On behalf of organizers, we thank our esteemed speakers, Professor Elgamal and Professor Charles Ng. It's indeed a great pleasure to be part of this particular session. And Professor Elgamal is actually a teacher of my teacher, Professor G.V. Ramana. Thank you, sir. Thank you very much. And also we are very much honored to host Professor Charles Ng. He is a president of ISSMGE. It is International Society for all the soil mechanics engineers. So our Indian Geotechnical Society is a part of ISSMGE. Thank you, sir, for sparing your valuable time and addressing our august audience. Thank you. And I also thank Dr. Reddy and Dr. Vishwas for nicely conducting the session. Thank you, all the participants for participating. And now I request all the participants to move on to the parallel sessions, which are going to be started now. Thank you, sir, one and all.
Thank you. Great to see you all.
Thank you.
Thank you. Nice to see you all. Thank you.
That was nice talk.
Yeah, thank you. And you gave an excellent talk too. So let's keep in touch. Okay, hope to meet you soon.
Yes, look forward.
Yeah, take care. Take care, everybody.
Bye-bye, everyone.
Bye-bye.
Bye. Thank you.
Bye.